use the. Okay. So last time we worked on the particle in a box problem. So first we did a one-dimensional box with infinite barriers, and then we extended it to a two-dimensional problem. So something like a rectangular box, a rectangular plane where the particle can move in a plane. And of course, you can also extend it to the three-dimensional problem where the particle is confined to a box. So we'll talk a little bit more about the 2D problem and then go on to the 3D problem.
Ma'am, I just had one question
Yeah.
before that. That
Yes, go on.
you had said last time that the way we constructed the Hamiltonian operator was saying the operator corresponding to Px is minus IH cross del by del x, and the operator corresponding to Py is minus IH cross del by del y.
Yes.
So, I mean, here we are assuming a priori that to measure something in the x direction is doing nothing to the y direction, and to measure something in the y direction is doing nothing in the x direction.
Yes. Yes.
So, can you just, I mean, maybe explain why? I mean, I understand this sort of intuitively, but can you explain why this is, I mean, really true in that way? I mean, this just happens like that.
Okay, so this was a question that was posed to me in the last class as well. I don't know by you or by someone else. So the thing is that the motion in the two directions are actually in reality independent of each other. So if you have a particle which is moving in a plane and you resolve its velocity or momentum into x and y directions, then you a priori assume that the x and y velocities are independent of each other. Now, this is true if there is only kinetic energy and there's nothing coupling the two motions. So
Okay.
so for example, if you had an external magnetic field, for instance, then this field would couple the x and y motion, because then the particle would want to go in a circle, right? So then the x momentum in the x direction limits the momentum in the y direction. In that case, you cannot use this Hamiltonian. Then there would be terms which involve both px and py.
Okay, so then, I mean, then actually this operator would not be I minus IH cross del by del x. There would be something else in addition to that.
Yeah, there would be one more term. So here it's just px squared plus py squared by 2m for the kinetic energy operator. Then the kinetic energy operator would also involve a px py term.
Okay, okay.
So it's because there is nothing coupling the two motions that these two motions are independent in this case.
Because V is zero, so we can do that, right? I mean, that is the logic we are using.
Yeah, here the potential is zero. Exactly. And in fact, it's not just because it's zero. If it was something that did not couple the two motions, like just some like an electric field, maybe like a uniform electric field in the x direction, that would also not couple the two. But something like a magnetic field would couple the two motions.
Okay, got it.
Yeah. So particle in a box. Okay. So let me recap the 2D box. What did so the box had a length of A and a breadth of B, and the Hamiltonian looked like minus h cross squared by 2m del squared del x squared plus del squared del y squared plus v, where vxy is equal to 0 for x lying between 0 and a, and y lying between 0 and b, and it was equal to infinity otherwise. And then we got the wave function solution as a function of x and y. And we only looked for solutions which were product separable because the Hamiltonian has independent x and y terms. Again, if there was a coupling between the x and y motions, then the wave function you could not assume to be a product separable one. Then you would need a more general expansion. Okay, so we found out that we have a wave function which is product of two sine functions, and it looks just like a product of two wave functions from the particle in a one-dimensional box. And we also generated two quantum numbers in this case, nx and ny. The energy also was found to be a function of both nx and ny, and that had the value h square by 8m nx square by a plus ny square by b. Okay. Now here we are asking a question. So can we have the same energy corresponding to different wave functions? Okay. Or let's say we can say that can energies of different wave functions be equal? So of course you see that it can be under the situation that nx square by a plus ny square by b.
Ma'am?
Yeah?
Ma'am, it should be a square and b square in the
Oh,
denominator.
I am sorry. Yes. The wave function has a, right? Yes, of course. Yeah. This should be squared. Is equal to some other set of numbers by a square by b square. So if these two are equal, but the numbers nx and nx prime are different and the number ny and ny prime are different, then your wave functions will be different, but the energies will be the same. Okay. So for two sets of numbers, nx by a and ny by b, if this is not equal to nx prime by a and ny prime by b, then psi is not equal to psi prime, but E is equal to E prime. Okay. In this case, psi and psi prime are said to be degenerate. Now, this is a term which comes very, very often in quantum mechanics. It's a special term which just tells you that the energies are the same, but the wave functions are different, or the states are different, but they have the same energy. Okay, simple enough. And this is the first time we encountered this in a 2D box. In a 1D box, we only had nx, so there is no question of degeneracy. And we drew the levels as well. There was only one wave function per energy level. But in this case, there are two. So before we draw it, we will consider a special case again, which is the square box. So if you have a square box, that basically means that B is equal to A. Therefore, psi xy is simply equal to 2 by A. 2 by A sine nx by x by A sine ny by y by now A. And E is equal to h squared by 8m. Now I can take a squared common. I have nx squared plus ny squared. Okay. Now if nx is equal to ny, then we have only one wave function, right? But if nx is not equal to ny, then we have an obvious degeneracy, which is what? Which is just reversing nx and ny. So let's say, which is nx equal to, let's say, n1, ny equal to n2. This is one set. And nx equal to n2, ny equal to n1. So these two are, this is sort of like an obvious degeneracy. Just between the, interchanging the two directions, x and y. So let's try to draw this. So I'm trying to draw the wave functions. So it is simple enough in the 1D case. In the 2D case, we have to be a little bit more of an artist. So we have the origin here. And I have the, let's see, how best to draw it. Not such a good artist. 1 second. So let's this maybe like this, x and y. Okay, and now I'm drawing the, so let's say I'm taking nx n1 equal to 2 and n2 equal to 1. So this is what I'm drawing. So if n2 means, so in the first case, so let's call this A, let's call this B. So now I'm drawing A. So nx is equal to 2 and ny is equal to 1. So if it's 2, then this is just like the n equal to 2 state of particle in a 1D box. So that's simply a sine wave along the x direction with one node, because n1 is 2, so number of nodes is 1. Now in the y direction, we have the quantum number 1. So this one has no nodes. So this looks like that. But the wave, so I can say this is y and this is xx. So what does the product wave function look like? The product wave function basically looks something like this whole space. So it's this undulated plane. Okay. So this is the wave function. So you can see the xy plane, and this axis along which I have put the amplitudes of my wave function, this is basically psi. Okay. So the z direction is the psi direction and xy is the coordinate space. So the wave function looks like an undulated wave in this case. Then let's try to draw B. Then B you can...
Ma'am, can you please just slightly go up?
Yeah.
Oh, okay, ma'am. I've got that. Thank you.
So now what you will have is the n equal to 1 quantum number in the x direction and the n equal to 2 quantum number in the y direction. Okay. And then again you can draw this wave function. Okay. This is my B. So these are two wave functions which look different given a coordinate system, and but the energies are the same. Okay. So this is the first time we encountered this. Now let's do the 3D box. So 3D box I will not be able to draw. So we will only write the wave function. So the 3D box will be a wave function which is a function of x, y, and z. And by extension, so again you can assume that the three directions are independent. So you have a product wave function x, x, y, y, z, z. So,
Ma'am, what will
yeah.
be the the general wave function psi x y t in case of the 2D box? I mean, for any general psi.
So you will have only one phase factor, because the phase factor depends only on the energy. And the energy for every psi xy, you have only one energy. You will
Okay.
have only one phase factor.
But then a double sum, right? Corresponding to nx and ny.
Oh, you mean for a non-stationary state? Yes.
Yes,
Then
yes.
yes. For a non-stationary state, you will have a double sum for nx and ny. Okay. So for a 3D box, by extension, I mean, it is quite intuitive. You will have again a product separable wave function, and you can follow the same process. And then you will get something that looks like two, let's say A, B, C box, 2 root A, B, C, and it will look like sine nx by x by A, sine ny by 1 by B, sine mz by z by C. And your E will now depend upon nx, ny, and nz. This will be equal to h squared by 8m nx squared by a squared plus ny squared by b squared plus nz squared by c squared. Okay, and you can see that when we go to the 3D box, my degeneracies will increase because now you have more possibilities. So if you have nx squared by a square plus ny squared by b squared plus nz. So if c squared is equal to nx prime squared by a squared plus ny prime squared by b squared plus nz prime squared by c squared, we get multiple degeneracies. And this is a very common question in both interviews and exams, where they give you a cubic box and they tell you to find out the sets of quantum numbers which give you degenerate wave functions. So then if it's a cube, then you can take a square equal to b square equal to c square. So then you have to just find out sets of numbers where the sum of the squares are equal, like different numbers. And also repeating numbers also give you different wave functions. So if you have a set which is 2, 1, 1, this is degenerate with 1, 2, 1, for example. So you can have repeating numbers which give you degenerate wave functions, and you can also find out different numbers. At the moment, I can't think of an example, but yeah, I guess you can find some as well. Okay. The other thing is, now for this model, we can find out expectation values, which gives me the properties of the wave function. So let's find some of them. So the first thing we'll try to find is,
Ma'am, if it's a a cube box, then the number of degeneracies for a particular energy, let's say 211, will be the like number of arrangements we can make with 211, right? Like
yes.
the permutations, combinations which we can make. So I think like 3 factorial divided by 2 factorial, something like that.
Yes, so here 1 is repeated, so yes. So you'll have some degeneracy for every energy level. Sorry, I mean, yeah, so for every energy level you can have more than one wave function by default. So for a 2D, like, you have at least a degeneracy of 2. And for 3D, you have at least a degeneracy of 3. So if all 3 numbers are different, then you can have 3 arrangements of these quantum numbers. So at least a degeneracy of 3. But again, if you have like a repeat of numbers, then that gets reduced. And if you have something like 1, 1, 1, then that is not degenerate. Just to consider. So this is a very common question. So just think about it a little bit. Like which ones are degenerate and what is the degeneracy. Okay, so the next thing we'll do is we'll find a few expectation values. What is the average position, let's say, of a particle in a 1D box? So we have to find out basically the expectation value of x. And the standard way of doing that is you take psi star, you have x, and you have psi, and you multiply over the volume element, which in this case is simply dx, and you divide by the overlap of the wave function with itself. Now, if this is a normalized wave function, you already know that this is 1. If it is not normalized, so if you're given an arbitrary wave function which you can see is not normalized, then you have to evaluate psi star psi as well. And we know the wave functions, you have a root of 2 by a. So from psi star and psi, you get 2 by a. And then integrate from 0 to a. So this is the general formula, so I write it again as this. But for the particular case now, I can restrict it to 0 to a. And I end up with x sine square pi x by a dx. So now we are doing it for the ground state. Notice I've already put nx equal to 1. Also, the quantum numbers for the ground states, they differ in the various problems. So, you have to be aware of that. So when it's the ground state of the particle in a box, then the quantum number is 1. But you will see when we do the harmonic oscillator, for instance, the ground state is n equal to 0. So be careful of that.
Ma'am,
Yeah.
ma'am, is that the denominator? I mean, what is that which is written below?
Which one? The psi star psi?
Yeah, the shy star shy dx part.
That's the denominator.
Okay.
And this is a normalized wave function, so I've put that value equal to 1.
Okay, ma'am.
Yeah. And then you can write 2 sine squared pi x by a as 1 minus cos 2 pi x by a, whatever. So I'll just write it short. This you will be able to do, I'm sure. Then you integrate by parts. Okay. By parts. Not working it all out, and you will find that the average value turns out to be a by 2. So basically, for the ground state, the particle in a 1D box, it has a expectation value which is a by 2 of x, which is a by 2. So so this is the average position of the particle. Now there is another alternative question that can be asked. What is the most probable position of the particle in a 1D box? So this may seem like a repeat question, but it is not. So in this case, you can work it out. So try it. So how do you think you will try it to find the most probable position?
Maxima of the probability distribution function.
Exactly. So you can do a maximum of psi star psi, for example, here. And then you can find out the value of x, the most probable position. I have not done this recently. As far as I remember, this for particular 1D box, you will still get a by 2. But this is not guaranteed for a quantum problem. So, for example, in the hydrogen atom, they are definitely different. The most probable position of the electron and the average position of the electron. But in this case, I think you will still end up with a by 2. But you can try it out. Okay. Then the other thing is, the other thing you can try out is find the expectation value of px. This is the other thing you can try. Now, for 1D. Now I'll do another thing. So I'll say find the expectation value of x and expectation of value of y for particle in 2D box. I just want to illustrate one thing over here. So here the wave function is a function of both x and y, but I am trying to find out the expectation value of x only. So you cannot have something like, well, you can, but it doesn't have much significance, which is the expectation value of something like xy. So what is more useful is when you keep the two directions separate and handle it as such. So that's why
All these questions are only for the ground state, right? Like all the previous questions
Yes,
are only
yes,
for the ground state.
yes, only for the ground state. Yeah, that you have to always be careful about. So for now, I am saying ground state, but someone might say excited state. It's not like you cannot do it. You can do it for the first excited state or second excited state. And in that case, if it's a 1D box, it's simple. It's just 1, 2, 3, 4. But if it's a 2D or 3D box, then you have to look at the sum of nx squared plus ny squared, or nx squared plus ny squared plus nz squared. So, and then you have to arrange it in order of energy, right? So then you have to be a bit more careful about which quantum numbers correspond to your first excited, and which one corresponds to your second excited. There's a chance to miss things in the middle. Okay, so where was I? Yeah, so I was trying to find out this one. Black one. Okay. Okay, let's say this is a square box. Ground state, square box. Make things simple. Then I can just write A Okay. Now remember, for a 2D box, they are normalized independently. So XX is normalized and YY is also normalized. And this is simply that condition. So this is equal to 1. And I end up with basically the same integral as the particle in a 1D box. And that I know is A by 2. Similarly, expectation value of Y will also be A by 2, because this is a square box. Is that fine? So if it's a 2D box, then and you're only taking the expectation value of either X or Y, then one part of it will always get integrated out to 1, and you will end up with a result similar to the 1D box. Now we have lots of time, so let's do the finite square well. Or should I do the harmonic oscillator first? Okay, maybe I'll do the harmonic oscillator. Yeah?
Ma'am, could you just scroll up a little?
Sure. This page?
Yeah, ma'am, here, do we need to, for the second question, do we need to find out the average value of finding the probability of X?
No, Px is the momentum operator.
Okay, the momentum. Okay.
Excuse me, ma'am.
Yeah?
In the 3D box, I think when we wrote the wave function, we made a small error. It should be 2 root 2 and not just 2. It would be 2 root 2 by root ABC. Because it will be root 2 by A into root 2 by B into root 2 by C.
Yeah, sorry. That will be 2 root 2. Yeah. That is right. I'm just considering whether I should do harmonic oscillator or finite square well. Okay, let's do a simple harmonic oscillator. Then it's less boring, and we'll do finite square well later. So I'll start on a different page. So we'll do simple harmonic oscillator. Now this is something you have done in classical physics before, I believe, in +2 or even afterwards. And what is it? So a harmonic oscillator is basically a mass on a spring system where the retarding force is proportional to the displacement and acts opposite to the displacement. Right? So it is something where you have a force that is proportional to minus x. If you displace this mass or particle in the positive x direction, then a force is generated inside the system which tries to restore it to the original position. So this force is written as minus kx, where k is the force constant or the spring constant. Now, in case of a quantum system, you don't have an actual spring, but but this sort of force or a restoring force can be present. For example, if you have a diatomic molecule and you stretch it a little bit, because of the Coulomb interactions, it would try to come back to the original equilibrium position. This is similar to a spring. So you can think of it like a spring, although there is no actual spring there. It is the Coulomb forces which are acting in this manner. But you can, but you use this spring model as a model. Okay, so you can model vibrational motion of a molecule as a harmonic oscillator, for example. So then, let's just recap the classical thing first, and then we'll go on to the quantum. This is this force constant or spring constant, and we know also that F is equal to mass into acceleration. So you can write minus kx is equal to mass into d squared x dt squared. And then if you solve this differential equation, you end up with a function of displacement. You end up with a function which is displacement as a function of time, which has the form a sine omega t plus b cos omega t, where omega is equal to root of k by m. So this comes simply from solving this differential equation. This is also similar to the differential equation we solved for the particle in a box as well. And also the energy of the system classically is known. It is a sum of the, someone wants to ask something? No? Okay. So the kinetic energy, and this is half m v square plus half k x square. So this is the form of the potential energy that you end up with classically. And so half mv square can also be written as p square by 2m, where p is the momentum of the particle. And then you can write this. And half kx squared can be called Vx, which is called the harmonic potential, equal to half kx squared. Okay. We can also write half kx squared as half m omega square x square. Now the advantage why we are doing this is we just want to keep the variables the same, or the variables the same as in the wave functions. In the wave function you end up with omega, so we are also writing the potential as omega here just to keep the notation similar. And once we have the energy in terms of the momentum and some functions of position, then we can go over to the quantum mechanical Hamiltonian by replacing P with the operator, and Vx remains as Vx. So then now we know the Hamiltonian for this system, which is P operator squared by 2m plus half m omega squared x squared. Okay. And I can simplify this also a little bit more. I can take m omega squared common, and then I end up with p squared by m squared omega squared plus x squared. Now x, whether you put a hat or not, it doesn't make much difference because it's simply a multiplicative operator. Now first we'll do something interesting. Okay. We'll do a solution in a very, very different way. We will not solve a differential equation like we did before. And then after that, I will show you how we get the same answer from solving the differential equation. Because otherwise it gets boring when you're doing the same thing over and over. So method of solution 1. Here we will use ladder operators. So-called ladder operators. I'll tell you what they are. Now, the first step will be that we will factorize H as V dagger V. So we will factorize it into a product of the same operator, but in a V dagger V form. Why do we want to do that? That this ensures that H remains Hermitian, whatever be the value of V. Okay. So this ensures that H remains Hermitian for all V. Now, why do we want to do that? Because if we can factorize H into V dagger V, then we don't need to check if H is Hermitian or not. And also it tells me that any Hamiltonian which is factorizable into V dagger V form is Hermitian. This is something we will do, and this will also help us solve the equation. Again, this is something that is a wise after the event procedure. So it's not like people knew as soon as they looked at the Hamiltonian that this is how you have to do it. Many people have tried in many different ways. And finally, this is what turned out to be the neatest and the nicest. So this is what you learn. But of course, this is not how it was discovered. So we will factorize it into V dagger V. Then, in order to do that, we will also need something like this. So see, our Hamiltonian looks like a squared by b squared. Looks like a squared by b squared. Okay.
Ma'am,
And if you want to, yeah.
Here V is the harmonic potential operator.
No. This is just some some
Arbitrary operator.
some arbitrary operator. We will find out what V is. Yeah. Okay, so now we look at the Hamiltonian more carefully. So it has basically a square plus b square form. Now we know that a square plus b square algebraically can be factorized into a plus ib into a minus ib. So this you see is a v dagger v form, for example. But we don't know for sure if this is valid for operators, this sort of factorization.
That is only if they commute, right? In algebra, they commute the real numbers. That's where that works.
In algebra, yes, everything, real numbers always commute. Any number always commutes actually. But once you have operators, that is not guaranteed. So you have to figure it out. So here actually we have p and x, which we know for sure don't commute. So we have to be careful and verify this. So we will verify this. Let's see. So our question then is wanted to write is x squared plus p squared by m square omega square, is that equal to x minus ip by m omega into x plus ip by m omega? That is the question. Now, if it is so, then we can, of course, directly factorize it. But let's see. So we look at the right-hand side. And what do we have? So if we open it out, being careful of the order in which the operators appear, we have x squared. Then we have the p square by m square omega square. Those are fine. But we have an additional term, which is basically minus I by m omega px and plus I by m omega xp, and that is equal to again x square plus p square by m square omega square. Then we have maybe I by m omega common and xp minus. Okay, I can just write it as a commutator, I guess. You are all comfortable now with commutators. So xp commutator. So what is xp? Xp commutator is equal to IH cross. This is minus H cross by. Okay. So, what have we got? We have got that x square plus p square by m square omega square is equal to x minus ip by m omega into x plus ip by m omega plus h cross by m omega. Okay, so we have an extra term here. So this looks like V dagger, if you like. This looks like V, but we have something extra over here. But we can still write. So we were not able to factorize it perfectly, but we can write our Hamiltonian now as half m omega square v dagger v plus h cross omega. Fine. And this can also be, so I can open this out a little bit because I want to cancel the m omega from the second term. Plus half h cross omega. Okay. So we did not manage a perfect factorization, but we did something quite close. So we isolated all the x and px operators into the first term, which looks like the factorized Hamiltonian that we wanted. The extra term that we have is basically just a constant. So that does not create a problem for us in solving things in this operator solution manner. Okay. So this is pretty good. Not perfect, but pretty good. So we can simplify this even further because now we have introduced two new operators. One new operator, V, but we need some more information about V. So we can find out some more things about V. Which is, the first thing is the commutator, which is very useful in quantum mechanics. So you have x plus I p by m. So I am omitting the hats sometimes, so that's nothing to be confused about. I'm just being a little bit lazy because I hate putting hats all the time. Here it's obvious, we're only talking about operators, so everything has hats. Okay. Then in this commutator form, x commutator is 0. Then pp commutator is also 0. The other commutators will remain, so we will have I by m omega px commutator, and I will have minus I by m omega xp commutator. This is, so px commutator is minus IH cross, so I have minus I by m omega minus I square h cross, and I have minus I by m omega IH cross. So this is h cross omega minus I square is plus h cross omega m omega, which is equal to 2h cross m omega. Okay. So we have found this. So VV dagger has a
Excuse me,
commutator which is
ma'am.
2h cross omega. Yeah.
Ma'am, can you explain how? Ma'am, can you explain how you expanded the commutator? I
Oh,
did not understand.
yeah. So there are 4 terms. So a plus b, comma, let's say c plus d. Then I just take them pairwise in order. So xx commutator, so I'm just keeping the commutator intact. Xx commutator, which I know to be 0. Then I'm looking at at this one and this one. There I will end up with.
Actually, this part was not properly done before. So if you would write in
We
detail,
don't know
it
how
would help
these
us.
operators actually work. Like this kind of algebra we are not used to, so it is very
Okay.
confusing.
So this is just a sort of short way of doing commutators. Ideally, you can write everything out fully and you will end up with the same thing. But okay, so if you have a commutator, then if you are careful about the order in which the operators appear, you can get them. Okay, I'll just write it then. Much better. Okay, let's see. So this is something that I will do aside. So there is a commutator and I have A plus B commutator C plus D. Okay. So then I can keep the commutators intact and take them pairwise. So you can have AC commutator plus BC commutator plus AD commutator plus BD commutator. So this you can do. Because if you had opened it out, then you would have got what? So long way. So the long way is A plus B comma C plus D. That is equal to A plus B into C plus D minus C plus D into A plus B. Right? This you know. And then you would have got AC plus BC plus AD plus BD, and then minus, then CA minus CB minus DA minus D, and then every pair will give you a commutator. So you get AC commutator from here plus BC commutator plus AD commutator plus AD commutator. So even if you had opened it out, you would have got the same thing. This is just a short way of simplifying. Is that clear?
Yes, ma'am.
Yeah. Okay. So now we have found that the commutator of V and V dagger, it is some value, 2H cross by M omega. Now what we will do is, since V is something we have defined on our own anyway, we will modify the definition of V. We will go from, we will modify the definition of V so that V, so we did V dagger, right? Yeah. So that V dagger commutator is equal to 1. So this is just to simplify our solution. Okay. So we'll go from V to V prime, and we'll so that the commutator of these two new operators is 1. And how will we do that? So we have 2H cross M omega. So we will simply do V is equal to root of, V prime is equal to root of M omega by 2H cross V. And V prime dagger is then root of M omega by 2H cross V dagger. And these two new operators, they are called A and A dagger conventionally. Sorry, A
Ma'am?
dagger. Yeah?
Ma'am, the previous part, actually, that's not very clear for me.
Previous one meaning this like how we expanded the commutator?
Yes, ma'am. This one, ma'am. Could you please explain this part again? I mean, I'm not understanding this. I understood the ABCD part, but when you're applying it there in the X and P cap operators, I'm not understanding it there.
Oh, okay. So it's the same thing. I mean, here, this is A. So this is A, this is B, this is C, and this is D. So the first commutator is AC, which is commutator XX, which is 0, because they are the same. Then commutator BC is this one. So this is BC. And this is AD. These are the two which remain. And BD is basically PP commutator, which is again 0. So commutator of the same operator is always 0, right? So those are the two zeros. Do you get it? Because
Okay, ma'am.
okay. Yeah, so now we have modified the definition of V. So we basically multiplied a constant with the V operator so that its commutator becomes 1. And these new operators, so I've called them V prime, but they're conventionally you use the letter A. And these A's are called creation and annihilation operators. You might have heard of them, you might not have heard of them. Okay, so this is a just a redefinition or multiplication with a constant. And then, therefore, we get two new operators where AA dagger is equal to 1. Okay. Now note that A is not Hermitian. A dagger A is Hermitian. Okay. So what have we here? So to summarize, what do we have? We have A is equal to root of m omega by 2h cross, and V was x plus I p by m omega. And A dagger is then root of m omega by 2h cross x minus I p by m omega. Okay. And knowing this, we can also express the x and p in terms of A and A dagger. So x is root of h cross by 2m omega, A plus A dagger, and p is equal to I root of m omega h cross by 2 A dagger minus A. Okay. So from 1 and 2, you can solve for x and p in a simultaneous equation manner, and you get 3 and 4. Then we summarize the Hamiltonian as well. So what did my Hamiltonian look like? We had got up to m omega square V dagger V plus half h cross omega. I guess, yes, this is what we had. And now I can write V dagger as root of 2h cross by m omega A dagger, and V is root of 2h cross by m omega A, and this just remains equal to okay, so we have m omega, so we have 1 omega left, and then you have 2 h cross, so that gets cancelled, so we get 2, here we have h cross omega, a dagger a, plus half h cross omega, and then we can take h cross omega common and have a dagger a plus half. Oh, so now you see the beauty of it, that it gets simplified to something quite simple, a dagger and a. Okay. Now we need to know how to solve now my Schrodinger equation with the help of a and a dagger. So to do that again, what do we need to know? We need to know what the action of a on psi is, right? So if you want to evaluate h psi, and h contains a and a dagger, we need to know what a psi and a dagger psi look like. So let's see. What is the action of a dagger and a on psi? That is our question. So a psi. We do it with the Hamiltonian and we figure out what a psi is. So if we have a wave function which looks like a psi, and then we have the Hamiltonian acting on it, then what is it? Then we have a dagger a plus half on a psi. Oh sorry, why am I putting hats on psi? That's not right. Okay. So h cross omega a plus a by 2 psi. So now I am going to write a dagger a in term as a dagger. Now we know since a dagger a is equal to 1 minus a dagger. This is from the commutator. Remember a dagger commutator is equal to 1. So, oh sorry, this will be the reverse then. So we have a dagger commutator equal to 1. A dagger minus a dagger a is equal to 1. A dagger a is equal to a dagger minus 1. So we use that here. And h cross omega is then a dagger minus 1 a plus a by 2 psi, and then this is equal to h cross omega a dagger a, so minus a plus a by 2 is minus a by 2 psi, and this is then cross omega. I can take a common, a dagger a minus half psi equal to a common H cross omega A dagger A plus half. So I'm trying to make it look like the Hamiltonian again. Okay. So A dagger A plus half, and I had minus half, so I can put a minus H cross omega over here. Psi. So this is equal to H minus H cross omega psi. Okay, so now I can act H on psi, and that will give me the energy E psi. So I have E, and H cross omega can remain as it is, psi. And now this is a number, so I can move this to the left, E psi. Okay. So what did we get? So we found out that, so what was the left hand side? The left hand side was simply H acting on A psi. So if I have a function generated by the action of A on psi, then I have found out the energy of that function to be E minus H cross psi. So what is then the conclusion? That A psi is an eigenfunction of the Hamiltonian with energy E minus H cross omega, which means that the action of A has reduced the energy of psi by H cross omega. Okay. So that is why A is called a step down operator. So it reduces the energy of the wave function. So it gives you a wave function with a lower energy. Similarly, if I do the same thing for H acting on A dagger psi, what I will get is basically E plus H cross omega acting on A dagger psi. So A dagger
Here
psi,
psi we are taking as the eigenfunction of the Hamiltonian in this case.
psi is an eigenfunction of the Hamiltonian with energy E.
Okay.
So psi is eigenfunction of H with energy E. Okay. That is H psi equal to E psi. This is satisfied. And then now if I act A on psi, then I get a new wave function, which is also an eigenfunction, but it has a lower energy. And we know by how much, so it's lower by H cross omega. And if I act A dagger on psi, then A dagger psi is also an eigenfunction, but its energy is higher than psi by H cross omega. So A dagger is then called a step up operator. And that is why A and A dagger, they are called ladder operators. They increase and decrease the energy of the wave function. Okay. So what is the advantage now of using such an operator? So now, provided we find one solution of psi, we can get solutions both higher and lower in energy by simply acting or a dagger on it. I said higher first, okay, so then a dagger or a on it. So I don't need to solve the Schrodinger equation multiple times. I need one solution of some kind, and then I can find out the others. Okay. Now remember that we had said that the energy of an eigenstate of the Hamiltonian cannot be lower than the minimum value of the potential that is present in the Hamiltonian. So recall that E must always be greater than V minimum of X. In this case, the minimum energy or the minimum potential is when X is equal to 0, and that is 0. Here, V minimum X is equal to 0. Therefore, negative energies are disallowed. So we know the ground state. So we can only, suppose we find the solution psi, and then we act A, which lowers the energy on this psi, so that we approach the ground state. We know which one will be the ground state. It will be the lowest positive energy. It cannot be negative. So it has to be, so we'll know when we reach the ground state. Thus, the lowering operator A must fail at some point. So what do we mean by fail? So by fail, we mean that it must destroy this wave function. So if you lower the ground state further, then the function must get annihilated, because a function with the negative energy cannot be an eigenfunction of a Hamiltonian whose minimum potential is 0. So we sort of impose that on this operator. So we say that A psi 0 is equal to 0. Psi 0 being the ground state. And what then this is called the annihilation condition. And then we go back to the differential equation form in 2 steps. So we know A is m omega by 2h cross x plus r equal to 0. This I can remove, that is a non-zero constant. So x plus h cross omega m omega. So p is equal to minus I h cross del x. Okay. And then minus I square is plus 1. Then h cross by m omega del x. Then psi 0 equal to 0. So we're going back to the differential equation. But this is a much simpler equation. See, this is a first order differential equation. And it only has a x as opposed to x squared. So before we had a second order differential equation and also a second, also x squared. So that was a more complicated equation. This is much simpler to solve, and this condition ensures that we have that A is a more physical operator, so it actually gives you the ground state eventually, and you can obtain it from this equation. Okay. So let's see, and we'll solve this later. Okay. Because we'll also do the differential equation method. We'll solve that then. But anyhow, this is the
Ma'am,
yeah.
Ma'am, I have two questions.
Yeah.
Ma'am, could you just scroll up a little where we have written H cap, A shy? That part. Ma'am, a little up.
Which part? This one?
Where we just started, what is the action of A plus and A?
Ah, okay. So here.
Yeah. Ma'am, how are we getting a minus half suddenly here? I could not understand.
Oh, here. Minus A plus A by 2.
Okay.
So here I'm getting minus A plus A. Oh, so over here.
Okay, ma'am. And ma'am, the other thing was when we were writing, when we wrote the final solution of this part, ma'am, from E minus H bar omega, why is it becoming E plus H bar omega? I mean, it's a real value, right?
Which one?
Ma'am,
So,
a little.
this
Yeah,
one you mean? Oh, this is a different equation. This is A dagger psi. So for A psi, you have E minus H cross omega. If I do the same thing for A dagger psi, then you will get E plus H cross omega.
Okay.
So this is fine. So this is finally the equation that we need to solve this one for the ground state. Now let's see if I can give you a little more background on why we need the annihilation condition. So let's see. I can call this maybe some additional justification for the annihilation condition. So let's see. So if I take the expectation value of h for the wave function psi, then this looks like this, and we have psi h cross omega A dagger A psi plus half h cross omega psi. And then h cross omega I can take outside. And when I move A dagger to the bra function, it will become A. So I will have A psi overlap. Then half h cross omega can also come outside, and I have a psi. This is a normalized wave function, so 1, and this is always positive. Therefore, h expectation value is always greater than or equal to half h cross omega. So this is what is called a lower bound on the energy. Okay. So, and for the equality to occur, what you need is, for equality, what you need is that A psi is equal to 0. Now this is only possible if A psi itself is 0. Okay? Right? Does that make sense to you? So the energy we can always obtain as an expectation or expectation value of the Hamiltonian, and we see that because we have this plus half h cross omega term, that will never go away. So that is the minimum energy of the system. And in order to attain that minimum energy, this first term, which is A psi overlap, this one will have to be 0. And because this is just an overlap, it's a square term, then the A psi itself has to be 0. So A psi definitely, so this is something that the operator A must satisfy. So we can now solve the differential equation. So let's solve the differential equation, which looks like this basically: d psi 0 dx is equal to minus m omega by h cross x psi 0. I think that, yeah, that is what it looked like. Yeah, so if I, so from this equation, so I'm writing del psi 0 del x and taking x to the other side. So that is minus m omega by h cross x psi 0. That is my differential equation. And the solution is psi 0 x is equal to some normalization constant multiplied by m omega x squared by 2h cross. So I'm just writing it directly here. You can verify it. And n0 is equal to m omega by pi h cross to the power 1/4. Okay. So this is then my ground state solution. And when I act A on it, it will become 0. And if I act A dagger on it, then I will get the higher excited state. So this is the ground state solution. This is the ground state solution. So you see, this method of solution is very different from the particle in a 1D box. In the 1D box, we got all the states in one go. So the wave function ended up with a quantum number in it, and by changing the quantum number, you could get higher and higher energies, and you got different wave functions, and it was all in one go. But here, we have only solved for the ground state wave function. We have not got the excited states yet. Okay, so how will we get the excited states? We need to raise the energy, so we will apply a dagger to it. Okay, so to get excited states, what do? We will do a dagger psi 0. This is what we need to find out. So every time we go up one energy level. So if we want to go up n energy levels, we need to apply a dagger n times. So I can say that the nth excited state. This is nth excited state. This has some normalization constant. I apply a dagger n times on psi 0.
I'm just one more clarification that the normalization will be done over all x, right? I mean, it's no longer confined to any x range.
Here it is, no, this is from minus infinity to plus infinity.
Okay.
Yeah, because this potential is this parabolic potential. So the x range is, so it looks like this, right? So this is Vx. So this the x extent goes from minus infinity to plus infinity. Okay, but I'll erase it here in case you get confused. Okay, and then with En, so every time it is h cross omega. So you start with half h cross omega, which is the lowest energy, and then you add n times h cross omega. So you end up with, sorry, yeah, so you end up with n plus half h cross omega. And this n then goes from 0, 1, 2, 3, up to whatever, up to infinity. So remember I had said that in particle in a 1D box, you see n is starting from 1, but in different problems it can start from a different number. So already in the harmonic oscillator, the lowest energy corresponds to n equal to 0. And then you have the first excited state with n equal to 1. And also the gaps between the energy states, they are exactly the same. They're h cross omega. Because this a dagger keeps shifting the energies by h cross omega at every step, the same amount. Okay, and if you normalize this, then the normalization constant an, I'll tell you what it looks like. Maybe we'll work it out later. It looks like 1 by root over n factorial. So let's actually stop here for today.
Ma'am, can I say that I think the speed is a little bit too much. I mean, we have covered lots of things in.
Okay, it was a bit too much. Okay. So then I'll use the next 15 minutes to just go over the rest. I'll stop here for now. I will not teach any more new things. I'll give you a recap of the harmonic oscillator problem. Okay. So let's go back. So I guess the particle in a box was phi. That is relatively simple. For the harmonic oscillator, okay. So the harmonic oscillator, we saw that it's a potential where the restorative force is proportional to the displacement but acts opposite to it. Okay. And the energy we take from the classical harmonic oscillator, it involves a kinetic energy term and a potential energy term. And we mimic various quantum systems as simple harmonic oscillators, which is why we're interested in the quantum version of this problem. And to go over to the quantum version of this problem, we need to express the energy in terms of momentum and position, because we know the quantum operators for these quantities. So we can do that easily because there's only a kinetic energy, which is p squared by 2m. And we have a potential which depends only on x. Okay. Then we started on a method of solution which is unique to quantum mechanics. That is the operator method. And in this case, it's the ladder operators. And these ladder operators find use in other quantum mechanical problems as well. So that's why we introduced them here. And it simplifies the way we solve the solution. So if we had a differential equation solution, we would have to solve this second order differential equation, basically, this one. But because we go over to this operator thing, you'll see it becomes much simpler. So to do that, the trick
Ma'am, but
is...
won't the solutions corresponding to the, I mean, the condition we impose that a psi 0 is 0 and then we raise it by a to the power n.
Yeah.
How do we know that these are, I mean, these constitute all the solutions? And I mean, let's say we have a non-stationary state, then also we can, I mean, express them in terms of this. Like, how do we know that?
Non-stationary states, are not covered by these ladder operators. I mean, you will only get the eigenstates in this
Okay.
case. The non-stationary, for non-stationary states, you never get a direct solution. You obtain the eigenstates, then you take the non-stationary state to be a linear combination of these eigenstates, which act as a basis, and then you evaluate these coefficients of every eigenstate. So that's
Okay,
the
so the
usual
wave
procedure.
functions we are getting by the ladder operator are also forming a complete
They are
basis.
also forming a complete basis. Yes, they are also forming a complete basis. Okay, so the real smart trick here was to try to express this Hamiltonian as a V dagger V form. Okay. So that was the smart idea, and that led to the discovery or construction, whatever you want to call it, of the creation of these A operators, which are very, very useful. Okay. So anyway, so what we tried to do was to factorize these operators into a product form. But in doing that, because these are not numbers and these are operators, we generated an extra term, half h cross omega. Okay. So when we tried to factorize this, which is present in the Hamiltonian, into this product, we ended up with an extra term over here, which was this h cross m omega. This h cross m omega eventually led to an extra term in the energy, which is half h cross omega. And this has a great physical significance. So I didn't give it a name before, but this is what is basically the 0-point energy of the harmonic oscillator. So the ground state cannot be a zero energy state for a harmonic oscillator. It has a minimum energy of half h cross omega. And this has significance in actual physical reality. So although it came from a very mathematical point of view, because x and p do not commute, the significance is physical, that you cannot reduce a vibrating system to zero energy. That's also related to not being able to reach 0 Kelvin, etc., etc.
So, ma'am, so is it something like for it to vibrate initially itself, we're providing some energy, and it cannot that energy that we're providing itself cannot simply go out anywhere. So that ground state will be there no matter what. You say.
Yeah, you're right. Yes. So that minimum energy is necessary to keep it as a harmonic oscillator. You cannot have it stopped in a way. Okay. So this is the extra energy term that we got, but it does not complicate my solution for the wave function because it's just a number. Okay. So we were happy with this, and we proceeded further to find out the properties of V dagger and V. The first thing we found out was the commutator. We found that it has a strange, bad value. So then we scaled the V operators to give me the A operators. And the A operators have a commutator value of 1. So that's how we scaled it. And we got these A operators. And the A operators are expressed in terms of x and p. So we can solve equation 1 and 2 simultaneously to get the x and p in terms of A and A dagger. Okay. Then what did we do? Then we wrote out our final Hamiltonian in terms of A and A dagger. And that has a pretty simple form. But we still don't know how to solve our Schrodinger equation in terms of these A and A dagger. So to do that, we tried to find out what sort of wave functions A psi and A dagger psi are. And when we used the Hamiltonian on the wave function A psi, we found that it is also an eigenfunction of the Hamiltonian, but it has a energy which is lower than psi by h cross omega. Okay, and then so the energy eigenvalue is E minus h cross omega for A psi. Also, if we use the wave function A dagger psi, we raise the energy by h cross omega. So that gave us a unique way of finding out the energy eigenstates and wave functions. And we decided to find out at least one wave function, and then we can raise the energy or lower the energy. Okay. And how to find out one wave function? What is the easiest one to find out? That's the ground state. And we said that since the A operators should not be able to go below the energy of the ground state, we can use an annihilation condition to find out the ground state, which is A psi 0 equal to 0. Okay. And by using this, we found out a differential equation, which is a first order differential equation. And the solution gave us the solution over here. It gives me the ground state of the harmonic oscillator. Now, since we simply want to find out the excited states now, we only need the A dagger operators. And to get the nth excited state, we use A dagger n times. Okay. And we get the excited state wave function. The energy is much simpler. So every time you increase by h cross omega, so the nth excited state is the ground state energy half h cross omega plus n h cross omega. So now we have the energy eigenvalues as well as the energy eigenstates of the harmonic oscillator. So afterwards we learn a little more about the algebra of A and A dagger, because that is very useful even for later studies if you go further in quantum mechanics. So there's a lot of interesting algebra that you can do with A and A dagger. So that is the next thing we'll do on Thursday. So I'll stop here for now.
Ma'am,
Yeah.
in the classical harmonic oscillator, something like a spring or some kind of real thing was giving us that potential, but not real in this is, I don't think this is imaginary, but in this case, what can be the thing which is giving us this kind of potential?
This is it's still the Coulomb force. So if you have, like I said, a diatomic molecule, for instance, and you consider that the two nuclei, they have they're bound by a bond through the electron. So you can mimic this bond as a harmonic oscillator. So the bond tries to keep the two nuclei at the equilibrium position. So if you either push it or pull it, it will try to get back to the equilibrium position. So the net effect of the bonds or the nucleus electron attractions, that can be modeled as a harmonic oscillator, for example.
Okay.
This can also be an external potential. So if you have something like a trap, if you have an ion trap, you might have heard of it in some talks. So if you want to trap an ion in some sort of electric field or electromagnetic field, that ion will also vibrate in this trap. So that is also a harmonic potential. Okay, so I guess we are done for today. Stop the screen sharing and the recording.